Hey everyone, and welcome. Today, we're diving into the world of engineering, but we're looking at it from two totally different ends of the spectrum. We're going to explore the absolutely mind-bending precision it takes to build things at the atomic level. And then, we're going to scale all the way up to the largest moving objects humanity has ever created.
So, that brings us to our central question. What could a tiny little processor possibly have in common with a ship that's as long as 3 football fields? It sounds like a riddle, right? But believe it or not, there's a surprisingly elegant answer that connects these two incredible feats of engineering. Let's start at the very beginning, at the smallest scale you can possibly imagine.
So, we're starting our journey at the nanoscale. And when I say small, I'm not talking about little screws or tiny gears you can see. No, we're talking about a world where we build things molecule by molecule.
And look, this isn't some far-off science fiction concept. Nanotechnology is happening right now. It's the actual science of engineering things at the atomic level, manipulating individual atoms to create materials and devices with totally new, almost magical properties. Think of it like this. We're using the smallest possible parts in the universe as our building blocks.
This is already in play. Take IBM, for example. They're using something called nanowires to cram 4 times more memory into the exact same physical space. And you know, it gets even wilder. Some researchers are figuring out how to replace electricity with light to send data. They're creating these optical circuits by actually slowing down light inside these tiny little silicon channels. It's incredible.
So, what's the end game here? Well, it's pretty simple and hugely ambitious. The ultimate goal is to build our most powerful computers ever from the smallest possible components in existence. This is a complete revolution in how we even think about building technology. Okay, so we've got these incredible nanoscale components, but how do they actually, think? Let's scale up just a little bit to the processors they create, the actual brains of our devices, and you'll find there are two very different philosophies for how to get work done. On one side, you've got the CPU, the central processing unit. Think of it as the specialist. It is built for speed and precision on single, complex tasks. And on the other side, you've got the GPU, the graphics processing unit. This is the workhorse. It's designed for pure brute force, tackling thousands or even millions of simple tasks all at the same time. So the CPU works through something called serial execution. The best analogy is a master chef. They are meticulously following a very complicated recipe one step at a time, in a very specific order. That's your CPU, making sure your operating system and all your programs run absolutely flawlessly.
The GPU, on the other hand, operates on a completely different principle: massive parallel execution. So instead of one master chef, I want you to picture an entire army of cooks, and they're all doing the same simple task, like chopping vegetables, at the exact same time. This is what makes GPUs absolute beasts for things like graphics, AI, and huge scientific calculations. I mean, just look at the difference in the number of cores. It's staggering. You've got maybe a few dozen really powerful cores in a CPU versus thousands of simpler ones in a GPU. The hardware itself is a perfect reflection of these two ideas: the specialist versus the workhorse. They are two different tools for two very different jobs.
Okay, so now I want you to buckle up because we're about to take a giant leap in scale. We've seen the complexity inside a computer, with all those specialized cores working together. But what happens when you have to build a complex machine that's designed to survive the most hostile environment we know of? Outer space. When you get right down to it, a satellite is basically a self-contained robot, a system made up of a bunch of other specialized systems. It needs a frame that's both super strong and super light. It needs a power source like solar panels. It needs antennas to talk to us back on Earth. It needs a command unit to be its brain, a guidance system to stay on course, and this one is absolutely critical: a thermal control unit to keep its sensitive electronics from either freezing solid or frying to a crisp.
And yeah, that really is the billion-dollar question, isn't it? I mean, you can't exactly send a repair person into orbit if something goes wrong. These machines have to work perfectly from the second they leave the ground. So, how do you guarantee that?
Well, the answer is you put it through absolute hell on Earth first. Satellites go through this brutal testing process. First, they're shaken violently and blasted with deafening noise to simulate a rocket launch. Then, they're stuck in a thermal vacuum chamber that mimics the crazy temperature swings and the total emptiness of space.
And finally, they go through pyroshock tests to make sure they can survive the small, controlled explosions that push them away from the rocket. Only if a satellite survives all of that is it cleared to fly.
All right, from the total vacuum of space, we're making our final jump in scale, down to the giants of our own planet. Let's talk about the largest moving objects ever constructed by human hands, megaships.
You know, there's this quote that I think just perfectly captures the magic of a shipyard. It's a place where literally tons of raw steel are transformed into these titans that are capable of withstanding the relentless power of the ocean for decades.
So how do you even begin to build something so enormous? Well, it's a bit like assembling the world's biggest, most complex Lego set. Instead of building it from the bottom up, huge plates of specialized steel are cut with lasers, and then they're assembled into these massive sections called blocks. All of the internal guts, miles of pipes, wiring, ventilation, are installed inside these blocks before these giant cranes lift them and weld them together with millimeter precision. It's just incredible to watch.
But it's the stuff you don't see that's maybe the most impressive part. There's this massive internal skeleton of thick steel beams that literally stops the ship from twisting apart in giant waves. Critical welds are scanned with X-rays to find hidden flaws. And the hull isn't just painted, it's covered in these high-tech coatings that fight rust, stop barnacles from growing on it, and even reduce friction in the water to save fuel.
And you know, this is a massive global industry, but it's really dominated by just a few key players. South Korea and China together account for about 75% of all the shipbuilding in the entire world, which is just a testament to their incredible industrial power. So after this journey across these truly vast scales of engineering, let's circle all the way back to our original question. What do all of these amazing things actually have in common? We started in the nanometer scale world of microchips, where we're literally building with individual atoms.
And we ended up at the nautical mile scale of a megaship, a floating city designed to battle the open ocean.
The blueprint is exactly the same. At every single scale, the principle is modular design. You take an impossibly complex system, and you break it down into smaller, self-contained, specialized modules. The thousands of cores in a GPU? They're modules. The pre-outfitted blocks of a megaship? They're modules. The power, command, and guidance systems on a satellite? All modules. Each part is perfected for its one job, then assembled into a greater whole, and then tested relentlessly against whatever environment it's going to face.
And that's the real takeaway here, isn't it? This blueprint for ingenuity, it's not just in chips and ships, it's everywhere. You see it in software development, in city planning, in logistics. The only thing that ever changes is the scale. So the real question is, now that you know the pattern, where are you going to see it next?